My name is Angnan Gu. I'm from the University of British Columbia, and we're here to present Pseudo-D informing multi-view uncertainty estimation with calibrated neural training dynamics. So what is the fundamental problem we're trying to tackle here? The deep learning algorithms typically have single view inputs. So for example, an image might be 224 by 224 by 3, and that's all the input you're getting. However, ultrasound datasets and many other medical datasets which involve cross-sectional imaging are fundamentally multi-view. When you train with one-hot labels, for example, for a classification problem, you are using the implicit assumption that each view has full information of the problem you're trying to solve. However, with multi-view, that might not be the case. It often depends on the cross-sectional angle, the image quality, and the anatomical visibility. For example, if we're looking at a problem where we want to visualize the aortic valve and clean input might have high contrast, it might be imaged at a correct angle, which means the aortic valve is fully visible. However, a noisy input might have low contrast and it might miss the angle that is required to image the aortic valve. Thus, if we pose a classification problem with a typical one-hot label, it might not apply to the same degree to a clean input and a noisy input. Thus, we propose a label augmentation technique and enables it to learn these uncertainties. In the first step of our training strategy, we make a crucial observation, and that is harder examples take longer to learn. What do I mean by that? If we have an easy example with clear visualization, the logits for the predominant class might be the first place in all the training iterations. However, that might not be the case for a difficult example with poor visualization, which has slower convergence and more disagreement between logits. When you take this into account, the training dynamics can help inform the sample difficulty. The next step of our training strategy is to compute the pseudo-labels. To do this, first we gather the training history denoted by f of xi at time step t and average across all time steps t. Secondly, we compute the pseudo-labels y'(i) with a technique known as Dirichlet calibration. We use the validation set to compute the calibration coefficients. For a bigger and more comprehensive description of the calibration process, please refer to our paper. Thirdly, we yield the pseudo-labels, which have an uncertainty that is scaled to the difficulty of the examples. What we're aiming for is for low-quality inputs to be hard examples, which lead to a more scattered pseudo-label. In our third step, we train a new model with the pseudo-labels, which are informed by training dynamics. The new model learns the behavior of giving low confidence for harder examples. For example, during inference, for a patient with significant aortic stenosis, which is our task, but a hard-to-see aortic valve, the model that was trained with pseudo-labels knows to yield a lower confidence score for the unclear acquisition image and to yield a higher score only for the clear image, avoiding overfitting. Our pseudo-label trained models have better calibration, which enables an improved fusion to study level. In terms of expected calibration error, our models outperform both the vanilla approach and other uncertainty estimation approaches. And in terms of study level balanced accuracy, our models are able to reach a higher accuracy due to the correlation between high uncertainty and low quality inputs. Thank you for watching our short introduction, and for more information, please refer to our publication.